here. Just give me a second. Okay, so supposingly, I think my U is actually negative x. My V is supposed to be x squared plus d squared over 4 raised to the power of 302. But I mean, this is supposed to be positive. Yeah, this is positive 302. Then, so this is minus minus. Yes, is plus. Okay. Then this is 3/2. Yeah, some correction here. So 3/2 minus 2 is half. Oh, sorry, 3/2 minus 1 is half. Sorry. Okay, so this is -1. Yep. So this would be half. So I would have to multiply with so this is equals to 0. Then I have to multiply with what here? So I have to multiply with square. Someone say something. Yeah, correct. It's correct. Yep. So I raise it to. So I raise it to this. So multiply both sides with d squared over 4 to the power of 3/2. Yeah. Then okay. So this is -1 plus 3x squared. So x squared plus d squared over 4 square. Right? Okay, before I go move on, just give me a second. I just want to make sure my working is correct. I don't substitute anything wrong. Okay. Okay, is this square root 3 x squared plus d squared over 4 whole thing square is equals to 1. Yeah. It doesn't seems like a quadratic to me. Just give me a second. After the ADX equals to 0. Yeah, I did that, right? So I erase both sides. I multiply, basically I just multiply everything by this term. So this will become 1. This will become square. So now I multiply with, now I make a square root of 1. So this 1 now. The blue color. Okay, Janwei, you have to tell me which term you are looking at. The first term or the second term? Okay. Yeah. Okay. Yeah. Okay. This is 302, yeah. Okay, yeah. So this is a 302 here, yeah, correct. So then, yes, then I have to multiply with negative 3/2. Then this become x squared plus d squared over 4, negative 2. Yeah. Then now, so now I can say that this is x squared plus d squared over 4 whole thing square plus 3x squared. And yes, so we have so we have 2x squared minus d squared over, is it whole thing square? No, sorry. There's no, not square, sorry. It's negative 1, sorry. Yep, it's negative 1. So I have d squared over 4. So x is plus minus d over 2 square root 2. Yeah, correct. Yeah. Okay. So that's the correction here. So as I said, I make a wrong substitution just now. I make a negative power here. So when there's a negative, so when I take negative power, then the differentiation they end up positive. Okay, second question. All right, so 2 point charges, each with 10 nanocoulomb, suspended by two string, and connected to the same point as in figure 2. So each charge has a mass of 10 to the power of negative 4 kilogram. Find the horizontal distance between the two charge with the assumption alpha is small. So we need to find what is the distance between the two charge. So assuming now this position is maintained because both are positive charge. So there is some kind of repulsion force in between them, and therefore this is static. Yeah, this position is static. Okay, so here is question 2 now. Question 2a. So how do we solve this? First, we need to know, okay, so assume that now the distance between the the 2 point charge here, the distance between these 2 point charge is x, yeah. So the distance between them is x. Then, okay, the string length is given. So first we assume, say let T is equals to, so let T be the tension, of the string, right? So therefore, uh, so T is the tension, okay? So if I resolve this vector of this tension in the string, so one is vertical and one is horizontal, yeah. So the angle made between the vertical component, and horizontal component. So let me just redraw this again, so you can see clearly here. So this angle between, I mean, these two vectors here is the resolved vector of t. So this angle here is alpha. So this is t sine t cos alpha. So t cos alpha and t sine alpha. Yeah. So after resolving, then equating t cos alpha So the mass here, there is some gravitational force exerted on the mass. So we have mg. So first equation. And T sine alpha. So which is equals to F, second equation. So so the force F, it is basically our electrostatic charge, which is K Q squared divided by X squared. Yeah. So using the electrostatic force term, and I said, okay, let let 2 divided by 1. Yeah. And substitute 3 into 2. So if 2 divided by 1, then on the left hand side it becomes tangent alpha. So K Q squared over X squared. So it's mg X squared. Okay. Okay, now. So how do we find the distance of X? So let me draw the triangle, this triangle here. The triangle, this triangle here. So this length here is 0.2. So I will call it L. So the length of the string is L. And this is X. And let's say this is the height here. So therefore tangent alpha is actually X divided by the height, right? And which is equals to X divided by square root. So no, sorry, this is not X. This is X over 2, sorry. So this is X over 2. So L square minus X square over 4. Yeah. And this will be X over square root of 4L square minus X square. Yeah. Okay, now, if alpha is small, so therefore if alpha is small, so this implies my L is much greater than X, right? If alpha is small, my L is much greater than X. And therefore tangent alpha is approximate as X over square root of 4L squared. Because if this is much greater than X, so the value of 4L squared minus X squared right, is going to be 4L squared. So x, so 4 times 2 times 0.4, yeah, sorry, 2 times 0.2, so which is x over 0.4 here. So remember L is 0.2. Okay, so I'm going to use this value x divided by 0.4 on my left hand side. So the k value q square mgx squared. Then is x cubed k times q square mg times 0.4. So k is 9 to the power of 9. 9 times 10 to the power of 10 to the power of 9. Multiply 0.4. Sorry, might multiply q square. Q square is what? What's the value? 10 nanocoulomb. Okay. So it's 10 nanocoulomb square times 0.4. What is the weight? What is the mass here? The mass is 10 to the power negative 4. Gravitational force, you can take 9.81. So what I have is 3.6697 times 10 to the power of negative 4. So raised to the power of 1/10, yeah? So it's 0.0716 meter. Okay. And lastly, so we have answer question A. Okay, lastly, a circular disk of radius um, between 1 to 2 meter is charged with a uniform surface charge density of 100 divided by r micron coulomb. So calculate the electric field intensity at a perpendicular distance 10 meter above the center of the disk. Okay, so this question is very similar to one of the tutorial question. Yeah, one of the tutorial questions. I think is question number 6 in your tutorial. But of course, this is hollow. Okay, because it says a disk of radius from 1 to 2 meter. So the inner radius is 1 meter and the outer radius is 2 meter. So assuming that, okay, so we can also apply, let's say this is 10 meter here. So let's say this height h. Okay, so we can also apply, I mean, we can exploit the property of symmetry, because again, even though the charge distribution now is rho s equals to 100 divided by r, right? So that means it's going to be influenced or affected by the dimension r here. So that means if I go further away, I mean, uh, at one, I mean, in between 1 to 2, right? Between 1 meter to 2 meter, um, even though it is affect, I mean, it is the distribution is different for each of the radius. But imagine if, let's say, you have a circle. I mean, you have a circular disc like this. Okay. So let's say you have a strip like this here. You have a strip like this. So regardless, again, if let's say you stand at this point at the height h from the disc, and then looking at the charge distribution. So from inner radius to outer radius, as I said, it is inversely proportional to the radius r. So even that, so as for other direction, as in other points of direction, they are the same as well. So here to here is also inversely proportional to 1 over r. Here to here also inversely proportional to 1 over r. And therefore, we can use the symmetry property as well. So that means when we evaluate the electric field at this point, so the horizontal component can be neglected because due to symmetry. So now, let's say this infinitesimal surface, the infinitesimal surface, which is r d phi, okay, infinitesimal surface, to be the point charge, to be as a point charge here. I mean, represent like a point charge contribute an electric field at this point. So we are going to integrate now. So therefore, E, the electric field at this point, at a height h from this surface integral, so R is actually h z cap minus r cap, yeah. And the magnitude of R, square root h square plus r square. Okay. So rho s rho s is 100 divided by r. Then r d phi and square root of r squared plus h squared, whole thing cubed, multiply with h z cap. Okay. Okay, r and r cancel off. So is 100 times h. So bear in mind h is 10 meter here in this case. So dr 3/2 multiply with d phi. So this is from r1 to 2 and 0 to 2 pi. Multiply, sorry, remember, multiply with 10 to the power negative 6 because the question says here is micron coulomb. Okay. So this integral here we always encounter. I mean, everyone should know this already. So E. So 100 times H is, so the integral for d phi 0 to 2 pi, the integral result is 2 pi. So I can simplify this further. So 100 times 10 meter, so it's 1000 meter here, divided by 2. So it's 500 epsilon. And this integral here, so if I use the appropriate substitution, I get, we should get cos theta d theta. If let's say I use a substitution for r equals to h tangent theta, yeah. So if I use this substitution here, so you should resolve it as cos theta d theta divided by h square, yeah, h square multiply z cap, so z cap multiply times 10 to the power negative 6. So h square is, h is 10. So h square is 100. So 500 divided by 100 is 5. Phi epsilon. And the integration of cos theta is sine theta, right? So for sine theta, based on our variable substitution, it will be r over square root r squared plus h squared from 1 to 2. So this 4 plus 100 is 1 square root of 104. square root of 101. So I get 54.633 kilo Newton per Coulomb. Okay, kilonewton per Coulomb. Or watt per meter. Okay, so this is the electric field in a direction of z cap. Okay, so that's it for the test, basically the solution for this test. Right. We are going to continue with our lecture. Before we start, is there any things that you would like to clarify regarding the test? Nothing to clarify? Okay, so I will upload this document. Okay, I will upload this document. So you can have a reference. So I will upload this document now, so you can have a reference. Study them. If you still, if you're still not sure, please study them. So if you have any doubts or, regarding the solution that I have just presented, please ask me. So we haven't started our lecture. You still can ask me now. Okay, so I will continue with the lecture if nothing else. So you can download it later. The solution I have just uploaded. Back to our lecture. So we have just a quick recap. Um, so far, what we have learned. So we have learned. So I want you to have like train of thoughts here. Like I mean, what is the I mean the progress. I want you to have the progressive thoughts. So now we have cover Coulomb's law. Coulomb's law. Then uh, for all the example that I have demonstrated to you, inclusive of the uh, inclusive of all the special cases that involve symmetrical property that somehow relates to Gauss law. Okay, that somehow relates to Gauss law. So Coulomb's law, we always assume that if it depends on the charge distribution geometry. So the charge distribution, how is it distributed? Is it distributed along a line? Is it distributed along, I mean, on a surface of on a flat surface, or is it distributed over a volume? So we assume, if let's say if it's a line, then we have to concentrate. We have to assume that the point charge. I mean, I always approach it. I always approach it that using an arbitrary point that behave like a point charge along the line, and then I proceed with the integration. So that's from Coulomb's law. Then we talk about then after that we talk about flux. So this is one. Then we talk about, before we arrive at Gauss law, then we talk about flux, right? So the concept of flux is just, if let's say we have a surface, the few lines that passes through the surface, okay, the few lines that passes through the surface as the calculation of flux. So flux is just the field, the electric field, or sorry, the electric flux multiplied ds. Yep. So if this is an open surface, so assume that let's say this is an open surface. So the flux from left to right that passes through the surface, if the flux direction is in the same direction with the normal direction to this surface, then the dot product here is a constant, and therefore we can straight away multiply with ds. Here I should put a note. If the direction, so this only implies that if the direction d is perpendicular to the surface. So it's perpendicular to the surface. Okay. So then the extension, this extension of the extension of the concept of flux, then we extend it to the discussion from Gauss law. So Gauss's law states that if we assume an imaginary closed surface, if we assume an imaginary closed surface in space, yeah, let's say you imagine in space you have an imaginary closed surface, the flux coming out from the surface the flux coming out from the surface is related to the flux coming out from the surface is related to the charge enclosed. So a closed surface, so the flux coming out from the surface, from the closed surface. So that's the difference. I put in the integral with a circle that represent a closed surface. Without the circle is an open surface. So I have basically I've given you a definition. What is a closed surface and open surface? Closed surface, imagine like a balloon, like a balloon. Open surface is like a piece of paper. Yeah, there's no continuity between all the edges. There's no continuity from all the edges, right? So if it's a closed surface like a plastic bag, like a balloon, that's the example I can provide to you. That's the closed surface. So the Gauss law relate to the charge enclosed by the imaginary surface. So this is Gauss law, and after that, I demonstrate to you using divergence and divergence theorem. Okay, and this relates to basically the volume of integration. The volume of integration. Okay, so the volume of integration is related to, so the charge enclosed, okay, is equals to the imaginary surface, this surface here, that enclose the charge density, right? So this volume, it is actually defined. It is this volume here is actually defined by the surface, by the Gaussian surface. So if let's say we have a spherical volume, okay, we have a spherical volume charge density. Then if you enclose it with a Gauss, with your imaginary surface, which is also which have a geometry of a sphere, okay, a Gaussian, a spherical Gaussian surface, then it is equals to the charge enclosed. And by applying the divergence theorem, and I have explained how the divergence theorem comes about, and here we arrive, rho v is actually the divergence of d, actually. So I will, so you can look back at the earlier notes that I have explained. So I have basically discussed what is divergence and how divergence theorem comes about. Okay, so all right. So we are basically at this point, at this junction. So we have apply Gauss's law for one example. So there are two ways. I've also demonstrated two ways. One is the integration, the volume integration of the uh, over the volume with um, volume charge density, and the other way is I use um, flux. Yeah. So both end up the same result. Yeah. One is the volume integration, and one is the surface integration with involved flux. So both came as the same results. Yeah. Both result the same answer. So that's actually proof the Gauss law, basically. So so far here's where, I mean, so far this is our where discussion ends last week. Okay, so I have give you a review. So I have provide you a recap of what we have learned so far. So please make sure if at any point here, if you do not understand, please ask me now. I mean, if you have any doubts regarding what we have discussed so far. So if not, I will continue with the lecture, with our with our discussion. So I let you have some time to think about mm, what you don't understand and you would like to ask. So no one have any questions? Okay, if you do not have any questions for now, uh, you can let me know later. Okay, so now uh, we will learn a new concept, but this is not entirely new to you. Perhaps, I mean, you should know what's potential, and but from from the circuit point of view, um, that you learn about Kirchhoff's law, then Ohm's law, and such is basically come from this generalization, from the generalization that you learn here. What you will that what we will discuss here. So Kirchhoff's law and Ohm's law basically derive from uh, based on the field, the electric field potentials. So which basically come from Maxwell, right? So from Coulomb's law, then the force, let's say the force uh, felt by a charge. Let's say we have a charge Q here. So let's say we have a charge Q at this point. So let's say I put a blue dot here. This is my charge here. So there will be a force. If let's say uh, the point charge is placed in these field lines, right? So you felt a force in this direction, which is the same direction as the electric field. Okay, so now imagine that from position B, I need to bring this point charge across the electric field lines to reach point A, from point B to reach point A. Okay, so the work done in displacing the charge uh, from for a short distance dl is equals to for infinitesimal length dl, okay, is equals to the force multiply the distance. So basically, if you look back at some analogy, if you look back at some analogy, if let's say you have a box on a flat surface, let's say you have an object, let's say a box on a flat surface, and in some way, let's say this is a force apply, let's say in this direction, let's say this is a force apply, so this is a box in analogy, yeah. So based on the force apply, the direction of force apply, so there will be, if we resolve this force here, so there will be a horizontal force and there will be a horizontal force and a vertical force, right? So if the box move to this position x, okay, so therefore the work done is actually the force multiply displacement of x, yeah, in this direction, yeah. So that is the work done. So same goes for displacing a point charge from one position to another position. And for infinitesimal distance of travel, the work done is actually the force multiply the infinitesimal of distance. But however, there is a negative sign associated with it, and this negative sign indicates that there is a external force, right? So what provide the motion of this, what provide the motion of this charge? So it could be from a battery due to, the battery chemical reaction and things like that. So that's one example of external force. So it can be any other external forces, yeah. So this external force, the negative sign represent the external force agent. So the total work done is then, so we are, so from the path A to B, so we represent the line, represent the line, the path, where bringing charge Q from point B to point A. So integrate over the path from A to B to A. So the potential, it is defined as the work done per unit charge. So here it is equals to the electric field, integrating the electric field over the path of where the point charge travels. So that is the potential. There's the potential differences. So if we consider that, if we consider, let's say, a point charge, so the electric field, let's say this electric field are coming out from the point charge. So the potential difference from point A to point B. So here, the integration, the variable of integration, okay, the variable of interest of integration is R, right? Okay. Okay, so why is it, here you can see that, why is it the dot product is only, it is only the R component. So the electric field here is defined as R cap, right? Is in, I mean, let's say the electric field that represent these field lines, the field lines here represent the contribution is represented by the point charge. But when dot dl, why is it only the R component? So anyone can remember what is dl, the differential length? If let's say it is in respect to the spherical component. So spherical component, we have dr, okay, in the r cap plus r sine theta in the phi cap component plus r d theta in the theta cap component. Okay. So that is for the spherical path length. I mean, if you're not sure, then please refer back to chapter 0, where we talk about the vectors, the analysis of vectors, and how this line, I mean, differential length that is associated with all these spherical coordinates, cylindrical coordinates, and Cartesian coordinates. So please refer back to that if you are not sure. So here are all the components. So however, when we perform the dot product, given that the point charge, the direction of the point charge, the electric field is in the radial direction. So if we dot product, and we know that phi cap, theta cap, it is perpendicular to each other, right? So the r cap, theta cap, and phi cap is perpendicular to each other, and therefore the rest of the product, the rest of the dot product is 0, because if two perpendicular vector, if you perform a dot product, it's going to be 0, except the radial component. Okay, so therefore we have this r cap dot r cap. So now then we reach to the point, okay, so we have to integrate over the dr variable, which is the radial direction from A to B. So the result here is basically the vector AB, the potential AB, which is the potential A minus the potential B. And bear in mind, the potential, there's no direction for potential. It's just a scalar value. So it's just regardless of which point, okay? Regardless, so if we see clearly, both are scalar value. So that means regardless which path that you took, the potential is always the same. So what I'm trying to say is, if let's say let's say this is your path B. Initially you take like this, A, right? So from B to A, this is your initial path, let's say. So regardless of which path you take, you can take like this, you can take like this, you can take like this. It will be the same. It will be the same potential. Okay, regardless which path the point charge has taken, how it arrived from B to A, regardless of which path it's taken, the potential is always the same, because it is a scalar. The result is a scalar value. So VAB is equals to VA minus VB, the potential point A with reference to B. So for a problem related to point charge, it is customary to choose infinity as a reference. So whereby the potential at infinity is equals to 0. So obviously, if from our result here, if we choose R tends to be far away from the point charge, then where RB is far away from the point charge. Therefore, the potential B, potential at point B is equals to 0 if R tends to infinity. So in other words, by assuming zero potential at infinity, the potential at a distance R from a point charge is the work done per unit charge by the external agent. So if the charge is not located at the origin, okay, so this is due to a point charge. If it's at origin, then it is R. If it's not at origin, okay, so the potential at any point, so this R prime here, it is with respect to where the point charge lies. Okay, so this R here corresponds where the point charge location, this R prime here. So this R here is the potential at any point with respect to R prime. So R prime is the reference point, which is not at the origin. So for n point charge, so if let's say we have different discrete point charge in space. So if we want to determine a potential at this point, it's just the superposition or the summation of all the potential contributed by the charge Q1, Q2, and up until Qn. And so if this correspond to discrete charges, yeah. So the formulation here, so from this formulation to here is basically employing the summation from 1 to n. Okay, so if you expand this, you get back what you have at the above expression. So this only for discrete charges, yeah, discrete charges. I should be more specific, discrete point charges. If it's a line charge, then if it's a line charge, surface charge, and volume charge density, then then come to the same concept where we apply for the electric field calculations. Yeah. So so this part here represent as the point charge, and then we have to integrate along the line to get the total contribution at a particular point of interest in space. And the same goes for the surface charge and volume charge density. So if the reference chosen is not at infinity, then we have to add a certain potential value, which is C. C is represent the potential of which is not at infinity. So C represents some potential value. So come back to Maxwell. In some way, there's another derivation for Maxwell. Since the potential between 2 point A and B is independent of path taken, which I just explained to you, regardless which path you from point B to A. So if let's say black path is the origin or the path of original, the initial path you have taken, the point charge has taken from traveling from B to A. So it is in actual fact, regardless of which point, which direction you choose, the potential is always the same. So it won't change any potential. So this is what it means. So if you take point A to point B and back point B to point B to A. So essentially, it is the negative value of point AB. Sorry, the potential of VAB is the same, is equals to the negative potential back from B to A. If let's say we take A to B, it's the same as B to A, but it's a negative potential. So that is, if it's a closed loop, if the path taken for the point charge, if the path taken for the point charge traveling from A to B and B back to A to B and B back to A is equals to 0. So for a closed path, this is equals to 0, right? So now, here we will, okay, I do not want to bog down with you. I mean the details. I don't want to go through all the details. So the Stokes theorem, I believe somehow you have, I believe you came across this theorem before in vector calculus. So I mean the definition of the curl. I mean this curl here. The definition of the curl is the limit of let's say delta S tends to 0 by definition, yeah, of the line integral of A dl. Okay. So this is the definition of the curl vector A. Curl of A. Definition of curl of vector A. This is the definition. Okay. This is the definition in vector calculus. The curl of vector A is equals to, basically is a measure of the circulation of a vector at a point. So basically what it means here is, if we define a path as an infinitesimal path, if we define an infinitesimal path like this, at point P, as shown in this diagram. So the path at point P. So this infinitesimal path, and we wanted to find what is the circulation at point P here. What is there any circulation? As the surface enclosed by this path, as the surface enclosed by this path tends to 0. Okay. So back to the potential difference. The reason why that if we take the potential from A to B and B back to A is 0, it is due to the fact that the electric field is not changing. So this only possible, the E field is conservative. So conservative means there is no change over time. Conservative. So the E field never changes over time. So when I say never changes, it means that regardless of the magnitude and direction at each point in space, the E field, it doesn't change. So it means that if I take a point here, and I measure a point here, let's say this is my point of measurement. So at time t equals to 0, I take a measure at time t equals to 0. It will be the same after 1 second the direction of E field must be the same at this point. The direction of E field must be the same at this point. The magnitude of at this point also must be the same. The magnitude of this point must be the same after, regardless of the time lapse, regardless of the time lapses. So it must be the same direction and magnitude must be the same. So if the E field is conservative, then yes, the resultant of the path integration, of E is equals to 0. So however, if the electric field is changing, then no, because if let's say we are taking the charge at point A to point B and back to point A. So at any moment when the charge is traveling, so there will be somehow of a resultant when there is a changing in direction and magnitude. So therefore that will be not equals to 0. And in fact, it will relates to somehow so for conservative field, yes, this is true. For conservative field, on the left hand side, the integral is equals the path integration, the closed path integration, bear in mind. So the integral here, maybe I write it down bigger. So the integral here, there's a circulation here. So if it's a conservative field, then the circulation of the path from one point to another point and back to the initial point, the resultant will be 0 if conservative field. However, this is only part of the story, actually. So we call this, therefore if the curl of vector E is equals to 0, because it's never changed, right? So as I said, the curl of E is a measure of circulation, right? It's a circulation, it's a measure of vector circulation. So I want to borrow back this diagram here. So if, as I said, if conservative field, the electric field direction and the magnitude is the same. So if this is our point of interest, so there won't be any changes. So assuming that your point P here, let me draw back here, maybe you can see better. So if I have an electric field in this direction, I just redraw back this diagram in the notes, this diagram here. So if I have a point P here, so assuming that you have a paddle, like a straw, or maybe like a flat plane like this. So if the magnitude is the same and the direction is the same, so this paddle here, it won't rotate. So for conservative field, it won't rotate, right? So there's no circulation basically at this point P. So, and therefore is equals to 0, the circulation. I mean the curl of E. If we measure at this point, the curl of E is equals to 0. So what about non-conservative? So this only happens if the electric field is changing in the direction as well as the magnitude. And this is where so I will just draw two lines here. So if let's say the electric field is changing now, so let's say the electric field start to change here. So let's say this point P now. If point P is located here, so one of the vector is pointing in this direction. One of the vector is pointing in this direction, and another vector is pointing in this direction. So therefore, it will rotate now. So if you have some kind of net circulation in this case, right? So if it's changing, this is one example I can provide you. So there are many other examples of how the direction and the magnitude of the vector and the direction of vector. So basically, it tells us that if the electric field is changing with time, which is non-conservative, then this equation is no longer true. So this is a second Maxwell equation. This is a second Maxwell equation only for electrostatic. Only for electrostatic. For generalized electromagnetic, for generalized Maxwell equation, this is actually equals to negative. So B represent the changing of magnetic field over time. So the changing of magnetic the changing of magnetic field over time, okay, that represent the curve of E, okay. So this is true. This will be the generalized Maxwell equation. Of course, there are other terms. There are other, but in general, this is the generalized Maxwell equation. But we haven't reached here yet. So B is basically the changes of magnetic flux density over time. So we won't cover this part here. So for now, this is fixed. I mean, this is where you should know. For our course, we only cover up until, the field that we encounter is only conservative. So this is where we will apply. So it's always true. This is always true when it is only for conservative field. But as I said, this is not the entire story. That's why what I want to say is only at this stage, we will take this as it is. We will take this formula, we will take this equation, Maxwell equation, as true, holds for, so I wish say only holds for conservative field. Okay, only holds for conservative field. So this one here is the generalized Maxwell equation. And yeah, but we won't look at the dynamic point of view. We will not touch the dynamic property of the magnetic field. So everything we study in this course is only static. So what about, then you may think, what about static, and what is the difference between, so what is the reason then? What is the reason then that we learn static? Why don't we straight away learn dynamics? So static as the static form as the fundamental that before you reach dynamics. So you have to learn static first before you learn dynamics. So therefore it's a stepping stone for you before you engage to the dynamic portion of this course. So there won't be dynamic So we won't be able to cover until the dynamic features for electromagnetics. So you need at least you need at least 2 semester course to cover everything. So this is only 1 semester. So we only able to cover static. And what is the implication here? Then you may ask, what is the implication here if I include, if let's say the Maxwell equation, the curl of the Maxwell equation include this term here. So what is the what is this implication that include this term here? So this implication tells us that the changes in magnetic field, okay, changes in magnetic field produces the curl of electric field over time, the curl of electric field over time. So the curl of electric field over time, and then if you the changes in electric field, then because this B is the magnetic field is never, I mean, it's not static, so it changes with time. So the changes in magnetic field produces changes in electric field. So therefore the circulation of electric field around the magnetic field. So it means that let me just illustrate this. So let's say I have this B field here. B field here. So it changes with time, right? Changes with time. And the electric field is circulating around the B field. If this changes with time, and the E field will change as well. The circulation will change. It will not always be in this direction. It changes in the other direction. So if this B direction and the magnitude is changing, so the circulation will always is changed as well. If the changes in electric field, on the other hand, the changes of electric field on the other hand will bring a change in magnetic field. Then that means it will induce a magnetic field from this point of view. And the changes in magnetic field, the changes in electric field will bring a change in magnetic field. So that means it will generate a magnetic field here, something like this. Okay. So if this changes, and then it will bring again a changes in electric field. Okay. And again, and this can be replicated many times. So what I try to illustrate here is that magnetic field change, B field change, result in a E field changes. Result in a E field changes based on this equation. Yeah, based on this equation. And this part we haven't learned yet. I mean, the change in magnetic field, the change in electric field, due to the fact that the B changes, this B field changes, will also result in a induced magnetic field. It result in an induced magnetic field. And the induced magnetic field is also changing due to the fact that E changes. And it will produce again, it will produces again and changing electric field, and so on. So what we can see here is actually a product of waves. So the electric field and magnetic field is waves, basically. This is the implication of this Maxwell equation. And with this discovery, with the Maxwell equation discovery, which discovered by Maxwell actually, which is, to be honest, there's another scientist, but it's not important here. So there's another scientist which is, um, I think is the pioneer, is than Maxwell, but nobody really knows about him. I will talk about that later on. Just a short story. So what I'm trying to say is the Maxwell equation uh, give rise to the potential at a time, which is many years ago, give rise to the potential of wireless technology, where now you have your handphones, your satellites, communications, right? Uh, Basically wireless communication. So this really enables this discovery of Maxwell, the four Maxwell equation. So this really gives rise to the potential of wireless communication. Okay. All right. So just now I mentioned there's another guy who actually will consider as the pioneer of this work. But however, Maxwell basically, nobody knows what is the actual story. Nobody knows. But this guy here is called the Oliver Heaviside. So Oliver Heaviside. So this guy here, Oliver Heaviside. So long time ago, is a self-made scientist. So he discovered many things actually, and one of them is he rewrite he actually rewrite Maxwell work in in a more proper manner and a more readable and more digestible compared to Maxwell. So, but no, but of course, the credit goes to Maxwell, even though Oliver Heaviside have contributed more. So that's just some story. So we never know. I mean, who has the hand on this discovery? Nobody really knows at the time. So again, I'm just trying to point out to you that the Maxwell equation give rise to the potential of wireless communication because due to this equation here, so the changing of magnetic field produces electric field, and the changes of electric field produces magnetic field, and so on, right? So that gives rise to the propagation of waves, of electric field waves and magnetic field waves, and therefore many property like many application was developed after that. Beside wireless communication, there are many um, about uh, space and defense. They have applied this. They have applied in radar and many more. Okay. Okay then. All right. So now, so from the definition of potential, okay, if so, this term here is actually the integral of dv, right? The integral of dv. So so the integral of dv, v is the integral of dv over the negative integral of dl. Yeah. So if you take out the integral, if you took out the integral term, so therefore the differential of the potential is equals to the electric field dot with the path taken. So if we extend this, if we extend this here with, so if you take E of x, E as E of x, there's x component, y component, and z component. Okay. And dl is the dx x cap plus dy y cap plus dz z cap. So the dot product of this, so the x component will be multiplied with the x component, and the dot product with other components will be 0. So ex multiply dx, ey multiply dy, ez multiply dz. However, this is on the right hand side. However, d of v can be represented as the total differential. So this is the total differential term, which is related to the partial differentiation. This is called the total differential term. Total differential of v. Okay. So now, if we compare the terms now, so on the left hand side is dv, which can be expressed as a total differential, and on the right hand side is the dot product of the electric field with the path taken. So comparing the same term, dx and dx, dy and dy, dz and dz. So comparing the terms, here we found that the x component, basically, the electric field of x component is a partial differentiation of v with respect to x, and y, if the partial differential, the y component is the partial differentiation of the potential with respect to y, and so on. So with a negative term. So if we from here we can deduce that E is actually the gradient of V, whereby the gradient, so this operator is a vector operator, bear in mind. So the gradient of delta is curly x cap, plus curly y cap, plus curly z cap. So it's a vector operator. So taking the gradient of V, which is the gradient of the potential, is therefore equals to the electric field. So bear in mind, V is scalar, is a scalar value. So if we take the gradient, so this produces a vector. So these equations show another way to obtain the electric field apart from using Coulomb's law and Gauss law. If the potential is known. So this property here, we will see, more application. We'll see some examples on how we approach the problem of calculating electric field based on the potential. And this happens in the subsequent chapters. I think most probably the next 2 chapters, that where we touch on Poisson and Laplace equation. Okay, so 2-point charge located at two different positions respectively. So find the potential at 101, assuming zero potential at infinity. Okay. So here, so V, so the formula for point charge, V is Q over 4 pi epsilon naught R, right? So if it's not in at the origin, then this is R minus R here. Okay. So we have to find, that means first we have to find the distance between these 2 points and then calculate. So let's say this is my point 1 and this is my point 2. Okay. This is the point of interest, P, let's say. This is my point P. So let's say R1. So R1 vector is point P1 to P. And point and vector R2, point P2 to P. The magnitude of R1. So this is square root of 6. Magnitude of R2. So 16 plus 9, 25, 26. And so now we can calculate V1, which is corresponds, this is my Q1, let's say this is my Q2, yeah. So V1 is negative 4 microcoulomb. Okay, 4 pi epsilon naught is, the value is 9 times 10 to the power of 9 times negative 4 micron coulomb divided by square root of 6. Okay. So this is equals to, so is equals to negative 14.96696, sorry, 697. Okay, 697 kilowatt. Okay, and V2, so V2 is 5 micron coulomb. With square root of 26. Okay. So this is positive 8.825 kilowatts. So total potential, therefore total potential at 101 is V1 plus V2. So negative 14.697 plus 8.825 kilowatts. So it's a negative 5.872 kilowatts. Okay. All right. So last example, given the potential V, find the electric flux density at D. So, okay. Um, so first for A, so for A, we need to find what is E first. E is equals to the gradient of V, yeah, the gradient of V. At this point, so the first we find what is E first, the gradient of V, negative gradient of V. I have to refer back to the formula. Just give me a second. There is a formula. Just give me a second. So for if you look at the coordinates given, I mean the function of potential given in this case, it relates to spherical. So I only need spherical, so I will so I only need spherical. Okay. Um Give me a second here. So now, so the gradient of V is equals to the electric field. So I need to find what is the electric flux at this point. Okay. So now, so curly V curly R. So this is equals to negative curly V curly R cap and plus 1 over R. Let me just, maybe we straight right away, yeah? We straight right away this. Therefore, E is negative. Curly V curly R is negative 20 over R cubed sine theta cos phi in the direction of R cap. Then add with curly V curly theta. So differentiate sine theta. Differentiate sine theta, I get 10 over R cubed. Differentiate sine theta, I got cos theta cos phi. And plus differentiate phi. So I get 10 over R cubed here. Differentiate phi, so it's negative. So this is theta cap minus sine theta, sine phi, right? So okay. So E, it is then 20 R cubed sine theta cos phi, 20 R cubed sine theta cos phi R cap minus 10 to the power of 10 over R cubed cos theta cos phi. Sine cos theta cos phi. And minus 10 divided by R cubed. Sine phi. Okay. So therefore, D is actually epsilon naught E. Right? So by substituting at this, at what point? 2 pi over 2, 0. So 2 pi over 2, 0. So at pi over 2, so if we take pi over 2, this is theta, r theta phi. So pi over 2, sorry, I missed the coordinates. I missed the vector weight. Sorry, just let me. So this is theta cap plus 10 over r cap sine phi cap. Yeah. So at phi equals to pi equals to 2, the first term is 20 over 2 cubed times 1 times 1, yeah, minus 10 over 2 cubed cos theta, 90 degrees is 0, so I don't have to see this. And this is theta cap plus 10 over 2 cubed sine phi. So 0, sine phi is 0, so times 0. I don't have to see this. So 20 divided by 8. Okay. So 1 over 36 pi times 10 to the power negative 9. So which is the free space permittivity. Multiply with, yep, 2.5. Yeah. So, so it is 22.2105 times 10 to the power negative 11 Newton per meter square. So it becomes 22.105 piconewton per meter square. So that's the answer. So in the direction of r cap. Okay, so it's already 4. So we will continue with the second part here of this question. So we will continue from here next week. I will post this. I will post the whole document since we only left one sub questions to complete. So I will post everything. Then I will continue from here. So you can have a revision at once at instance. So before we end, I would like to ask again one more round if you have